All right, welcome to another video, families of exponential functions. We're still talking about 1.4 in Stewart's Calculus Early Transcendentals. So in this video, we're going to try to distinguish between exponential function graphs and identify decaying and growing behavior. So our general ideas with exponential functions. So what is true of all of these functions? We know that we're looking at functions of the form f of x equals b raised to the x power, where b is greater than 0. My apologies for changing the variable here, but b for base, right? We have a function or a class of functions, class/family, with a domain of all real numbers. Its range is 0 to infinity, not including 0. So that is for all real numbers. B raised to the x power is always going to be greater than 0. It cannot be negative, and it cannot be equal to 0. Okay, so that's actually going to be really helpful later on in this course and beyond. So what distinguishes these functions from other functions are things such as always passing through the point 0, 1, and it's always monotone. So it's always either increasing or decreasing on its whole domain. And we have two fundamental different types. So the first type is what we call exponential growth. Our prototype here is going to be y equals 2 raised to the x power, which we've already seen, and y equal to 4 to the x power. And remember, the base can be any real number, so it could be 4.5, it doesn't matter. Now let's graph these. We're going to loosely sketch these. And the important thing here is when we are capturing their behavior, it's going to be hard to graph more than just a few points. So, for instance, for y to the 2x, actually, you know what? Let's do 2 to the x, whoops. Let's do, oh geez, here, let me start over. I'm going to use different colors so that we can distinguish between them. Okay, let's start with some cool colors. So y equals 1.5 to the x power, okay? And then we're going to do 2 to the x power, and then let's do 4 to the x power. Okay, that should be okay. So our first one, right, is 1.5 to the x power. So remember, these pass through the point 0, 1 always. And then the next one is going to be, when you plug in 1, you should get 1.5. So notice another consequence is that it always passes through the point 1, comma, b, where b is the base. Okay? As well as negative 1, 1 over b. Okay, so to try to capture that, let's try to think about what this should look like. 1.5 squared, right, is going to be right around here. So this one grows not as fast, but it will eventually grow very fast. The next one, y to the 2x, should grow even faster. So at first it starts out slower, but then it quickly grows faster. And similarly, our last one, y to the 4x, well, we just shoot up to very large numbers very quickly. And so you'll see when you graph these, either on Desmos or by hand, it can get really unmanageable really quick. So exponential growth. One thing to note here that we'll come back to later is that these functions grow faster. And I'm going to put that in between quotation marks because we're going to make that precise later, than any polynomial or power function. Yeah, it's super cool. So that's exponential growth. And what distinguishes these is our base is always going to be greater than 1. On the other hand, we have what we call exponential decay. And that is distinguished by taking bases less than 1 but greater than 0. Oh, notice, yeah, these are always increasing. Oh, we talked about that. Yeah. All right, let's try some other colors here. Let's go with some yellow. So we'll do y equal to 0.75 raised to the x power. And we'll do y equal to 0.5 to the x power. And how about y equal to 0.1 to the x power? So remember, these are numbers smaller than 1 that when you raise them to higher powers, you're multiplying by something smaller than 1, so it shrinks the value. So we'll graph these. Wait, did I grab the right color? Here we go. Okay. 1, 2, 3. -1, -2, -3. Okay. So these are going to be different because, as you know, they will still pass through these points. For instance, if we focus on 0.75x. But now, because this is something less than 1, we should think about this in terms of this is 3 raised to the 4th power. Sorry, 3 over 4 raised to the x power. And that means that if we plug in -1, that'll flip it, and we end up with something like 4/3. But then plug in 1, and you get 3/4. And that'll just keep going down. Plug in it again, you get 9 over 25. Plug in -2, and you get something like 25 over 9, which is roughly 8. No, 25 over 9. That's not 8. That's almost 3, 2 point something. Okay, so it looks more like this. (0.5) on the other hand, right? So again, it passes through 0, 1. It'll pass through 1.5, 2.25. It'll pass through -1, 2, -2, 4. Notice that it looks like a reflection of 2 to the x. And lastly, here we have 1 over 10 raised to the x power. And this is just going to be completely impossible to graph accurately, because it just shoots up way faster than the other ones. Because you know it should pass through the point -1, 10. Okay, so some things to note, always decreasing. And we will say it decays faster than any polynomial or power function. Again, we'll make that precise later. And there's a special case here that we want to think about, which is what we call the natural exponential. and this is going to be a recurring theme, that we define the natural exponential as let f of x equal e raised to the x power, where e is a number, such that the graph touches a line through 0, 1 uniquely with a slope of 1. This sounds weird. Let me explain what this looks like. So, actually, yeah, okay. So, if we want to imagine this exponential, right? Remember that all of these exponentials pass through the point 0, 1. Let's call this 0, 1. And so it looks like this, roughly. But this is special in that this is the one exponential function that when you pass a line right through that point, touching that graph uniquely at one point, this line has a slope equal to 1. Bizarre, okay? So intuition, what does this actually look like? If we actually play around with this, we'll find that this number is roughly between 2 and 3, because 2 raised to the x power, the graph of that, sandwiches e raised to the x power, along with 3 raised to the x power. So you would find these two graphs of y equals 2 to the x and y equals 3 to the x containing this graph right between it, okay? And we approximate this number e as about 2.71828, okay? So this number e, called Euler's number, defines the natural exponential function as its base. And one of the interesting and bizarre implications of E is that it comes up time and again as we explore calculus, in that we can define it a bunch of different ways, and in ways that you wouldn't expect. So in a future video, we'll talk about some of the implications of modeling with these functions.